Hello, I'm Crystal Grotman.
I'm Darren Cole, and today we're going to be talking about projectile motion with air-resistant using vpython.
This problem was presented to us by our professor, Dr. Marble. So let's get started. So we were given the problem of a projectile motion of a ball starting at the origin of a coordinate plane. So we are going to draw this out. We are going to draw our coordinate plane of our x and y axis and a ball. So if a ball is here and is going to be projected, it is going to make a quadratic parabola. Now, there are two forces acting on the ball as it is going through the projectile motion. The first one is gravity, and the second one is air drag. If we are going to draw a free body diagram of the ball in any state of this problem, it will be a sphere, the force of gravity acting on the ball with the negative force of negative 9.8. Now, the drag force is going to be an opposing or going in the opposite direction of the velocity of the ball. So we are going to draw the ball up here. We have a velocity vector that is going to be tangent to this curve. So this is the velocity of the ball. The force of drag is going to be pointed in the opposite direction of the velocity. And I will label the force of drag F of D. When I put this into my free body diagram, I'm going to divide it into its x and y components of the force. So we're going to have the F, we're going to have the force of drag in the x component, and the force of drag in the y component. And then of course, we're going to have our y going in the positive direction, our x going in the positive direction to the right. Of course, we know that there is going to be a force of drag due to Stokes' law. Stokes' law says and states, when any object rises or falls through a fluid, it will experience a viscous drag. This viscous drag is going to be the force due to the Stokes' law states that the force of drag is equal to negative 6 pi times the viscous of the fluid times the radius of the sphere and times the velocity of the sphere. So you will see this formula again presented in our code. We're going to be using vpython for this problem because it limits the amount of errors presented in the problem. Again, we're going to be using vpython to this will allow us to prevent any problems with integers division and avoid any complications when handling the math.
Alright, so like Crystal said, using vpython to solve this problem will present integer division with complication. So here's our code. So we have the ground. The ground is the creation of our launch pad. And then we have the ball. The position is 0, 0, 0, radius is 0.5, and the color is red. In this section with the inputs, this part of the code is to use to gather input information from the user. So we got M, which is our mass. We have V naught, which is the initial speed. We have theta, which is the launch angle measure with respect to the x-axis. We have the radius, which Dr. Marble gave us, which is 0.5 for both balls. And then we have our viscosity of the fluid. So here, this is where you see V naught times cosine times theta times pi divided by 180. So that's going to be the x-axis. That's going to be the x-axis. So like she was saying, with the drag with the x-axis. Then you see v naught times sine times theta times pi divided by 180. That's going to be the air drag for the y-axis. All right, so here's the initial condition. We have t equals 0. T equals 0. dt, which is 0.001 or 100th of a second time step. The FG, which is our weight, notice that it is negative 9.8 times dt. That is the reason, because to change the, this is showing where it's going to be. So that's why we use vpython that way, because we wouldn't be able to show it with us being human, but vpython is able to show that within that certain time. Notice that I have max h. That is going to represent our max height. But I'll demonstrate that later while we go to the while, which is the loop. Airtime starts at 0. All right, so here's our while. This is the most important of our code, the loop. My rate is 2,000. So that's basically saying that while the time step, which is the change of time, which is 0.01, that's basically giving it the motion. So if it's too fast, if it's too slow. So my 2,000 was just enough to even get it the perfect motion in my code. You got our Y1, which is the ball position. We got our ball.v, which we need to be, it needs to be as a vector, and we need to know where it's going. So that's what that means. And for our time, it needs to be times the change of time. And then our if statement, that's basically saying if y1 is greater than y2, then our max would be y1. So it's still going to calculate as it's going up. As soon as it starts curving down, it's going to show us our max. And then that's why I have those print statements down there showing that our time, ball traveled, showing that the ball maximum height, and also showing that the ball's air time, which is in seconds.
Provided these three print staples are going to give us the possibility to compare, because we're going to have two separate codes, one with air drag and the one without air drag. The one we are going to show you right now is one where we are considering air drag. So we were given a mass of 6.2 kilograms. We were given the initial speed of 41.2. The degree from the x-axis is going to be 51.2 degrees. Our radius is 0.5 meters. Our
Disgusting.
of the fluid is going to be 0.55.
So notice that, like I said, I printed out my time travel. So this is approximately 170.1 meters on the x-axis. The ball maximum height is 0.026, approximately 0.026 meters. And the ball's air time, which is starting at 0, ended at 6.55, approximately 6.55 seconds. So going to our next code, which is air drag. Alright, so our next program, I tried to do it together, but I'm not understanding why vpython wouldn't allow me to do it together, so I just did it on separate codings. So this one to our left, which is our green projectile motion, this one is with no air drag. So they're basically the same thing. I created my same launch pad, same stretch, which is 300. The radius of the sphere of this one is the same, which is 0.5. Same inputs, but what's different about this one is this one has no air drag. So,
so both of them are going to have a mass of 6.2 kilograms. They're going to have an initial speed of 41.2 meters per second. The degree of, with respect to the x-axis on both of them is going to be 51.2 degrees. The radius of both spheres is going to be 0.5. And then the viscosity of the fluid is going to be 0.55 for both.
alright, so on the right, which is our red air drag, which is the red one, which is air drag, which is ball travel was 170. The maximum height was approximately 0.27, and the air time, which was 6.55. Over here to the left, which is our green one, you can tell there's a difference. The ball travel was 166.5 meters on the x-axis. The ball maximum height was 0.26, so it's a slight difference in meters. And the ball air time was 6.76. So it took a little bit longer for the green one with no air drag than the red one.
So what he's saying is that without air drag, the time was less than the time with air drag. So the time went from being 166.54 seconds, and the time with air drag was 170.1469 seconds. So as you can see, there was an increase of time there. There was also a decrease in the max of height. So without the air drag, there was 0.26 meters of a maximum height, and with air drag, there was a 0.025 meters of a maximum height. So there is approximately a difference of 0.001 meters. Now the ball's air time also decreased with the amount of air drag included. So without air drag, the ball's air time was 6.76 seconds, and then the ball's air time with air drag is 6.55 seconds. So the air time has decreased. We're going to show you these programs one more time. So if you saw through the video, I know it's hard to see because there's no way that we can possibly start them at exactly the same side because they're on two different codes. But if you looked really closely, what we saw was that the green one took longer to land, or the red one took longer to land than the green one. Now, I do understand that it's hard to see because they're on two separate programs, because that is what we wanted to accomplish by showing you the video the second time. So today, what we proved to you is that whenever you add air drag into a projectile problem, there will be a a increase in the amount of time that it takes for the ball to travel, a decrease in the maximum height that the ball will be able to reach, as well as a decrease in the amount of time the ball will have in the air.
I'm Adirian.
And I'm Crystal, and I hope you enjoyed our project. Thank you.